So thank you for the introduction. Good morning, everyone. Today I will be talking about knowledge engineering in chemistry. Knowledge engineering aims to emulate the decision-making process of domain experts. And in this presentation, I will discuss about rational design of meta-organic polyhedra. Why do we look at the rational design? Because in molecular engineering, most of the time, when we plan a new experiment, or for example, when we design which structures have to be calculated next, you need to make a concept based on that will be rational. And why do we bring meta-organic polyhedra? We bring because in this case, the rational design has to consider two things. It has to consider the chemical complementarity, that means between functional groups, but it also has to take into consideration the overall topological compatibility. So this project was developed by me and my colleagues at a group of Professor Kraft at the Department of Chemical Engineering and Biotechnology in Cambridge, the CMCL company also in Cambridge, and the Cambridge Cares Institute in Singapore. For this work, we have written a technical report, a preprint 292, which is currently available at the COMO webpage, in case you would like to read more. So these days, we discuss a lot about chemistry and AI, but some 30 years ago, the discussion was, of course, raised by Roald Hoffmann and others, what chemists really should aim at. And at that time was, do we really want to make molecules which are very mimicking the nature as we know it, or we want to focus on the ideal structures, something that would be very Platonic, but probably may not give some application directly. So what has happened over the past decades is that it becomes more and more evident that highly symmetrical structures actually can be also functional. And you have here, for example, some examples, also synthetic ones, like the capillaries, or for example, the capsid structures in viruses. The question is, how can we make them, more of them, and in a scalable manner? So meta-organic polyhedra is some field that was developing over the past 20 years. And a MOP is built of normally a metal-oxo cluster, like the inorganic cluster, and it's also built of organic secondary building units. So these two units come together and build this polyhedral species. So this meta-organic polyhedron has an associated polyhedron. In this case, would be the icosahedral structure. They have been reviewed originally by Omar Yagi in 2008, but we have more recent reviews from 2021 and 2020. MOPs are good for catalysis, gas sorption, and host gas chemistry. And they, of course, show similarities to other systems, like discussed this morning, for example, the meta-organic frameworks, polyoxometalates, and meta-organic cages. How do we design MOPs? So one way, the human way approach would be, well, we have a domain knowledge. We know so many structures of MOPs. And we can think about how their building blocks, the secondary building units, basically are compatible with each other. But then we have to consider the spatial thinking. And I will come to that in a moment. This type of approach is good, especially when you run structure after structure. Chemists can come up with ideas of secondary building units. They can be very interesting, and then they can give special functionality to the final MOP. But this approach is low throughput. It requires really to consider multiple things at the same time. If we go with the knowledge engineering approach, for example, as it is implemented in the World Avatar, and I will come in a moment also to that, we actually combine ontologies, which shows the interconnection of concepts between and relations. Then we have instances, which would be the relational data of different MOPs and their building units, and it comes an agent, software agents that solves a particular problem. The advantage of this is that it can be scaled up, it can go high throughput, and we can actually reveal the chemical space that is reasonable, that is actually useful to people in labs, and also, for example, to people who may do DFT, because the suggestion is what a chemist would suggest. So if you look at the reviews, and those reviews contain information on the reported structures, that is experimentally verified structures, we define the known chemical space of MOPs, let's say. But this chemical space of MOPs is based on known building units. But those building units can be still used to design new MOPs which have not been reported. So the idea, we will need to extrapolate this in some way. If we build new structures of MOPs based on completely novel design, which we don't know about and we don't know if those are synthesizable, then we will go to the deep chemical space. So this presentation actually deals with the immediate chemical space. And we want to have that because normally there are some criteria in theory that you would like to fulfill to define if a structure is, let's say, theoretically viable or not. So it can save also work for calculations. Using this type of these two reviews, we can curate up to 100. We can curate in a clean fashion 137 secondary building units, and we can see that we have 151 MOP assemblies. The question is how many new we can derive further. So far, I have shown that basically we can. What is the state of the art? The question is, how do we bring the thinking? How do we actually go towards how chemists may think spatially? And one way to do it is basically to think about toys. So before working on this project, I used to develop a toy for chemical didactics. These are the programmable interlocking disks. So these structures can be basically used to model a variety of meta-organic frameworks, polyhedra structures, nanotubes, and so on. And they work in a very similar fashion. You take a little toy, you build something like a symmetrical block, secondary building unit, and from there you actually assemble those in a model. This was actually originally inspired from polyoxymetalate chemistry, and we actually have a lot of those type of structures models that have been derived. Now, the good point about the programmable interlocking disk is, first, children love it. We create a lot of structures, but what we learn, point number one, especially when children use it, they are able to discover polyhedral topologies without mathematical pre-knowledge. They are able to design, for example, a tetrahedron without knowing that, having seen this before. The other point is that people know when they hit a limit, because the toy has some, when you design, you hit some strains, so you develop this so-called Fingerspitzengefühl. You get the fingertips feeling if the structure is stable or not. So ideally, you would like to take these things when you design algorithm and ontology. The next point that we see, and this is where the schism comes, normally in this type of chemistry, people used to have the concept of secondary building unit. Now we see that the secondary building unit, essentially, these are two concepts. We have a chemical building unit, chemical information, and spatial information. It would be the generic, not spatial, geometric and, information which is used within the generic building unit. So this actually gave us some confidence to go further and to develop a concept on assembly models. So we have a MOP, and instead of secondary building unit, we look at two different now chemical building units, CBUs. These CBUs function as generic building unit. The MOP at the same time has an assembly model, and this is the abstract, let's say, representation or the blueprint of that MOP. The assembly model has generic building units. At the same time, the assembly model has a generic building unit number, which is the number of the generic building units. So what actually this allows us, it allows us to have many MOPs, and then suddenly they are being clustered as an assembly models. So we are able to see them through the prism of the assembly models. And it's also, to some level, possible to derive assembly models. For example, just looking at these type of Platonic shapes, we can basically derive in a very straightforward the assembly what would be the possible assembly models. And we also see from there that the generic building units you get something like 2 modular, like band, and so on, and that they are being used. Now, from all this picture, you may consider, well, there are only 8 generic building units, but this would be false. So, for example, when you look at these 2 band, it can have a different dihedral angles. And this is not being encoded. So it's not hard encoded what would be the angles. The question is, how can we make this in a way that algorithm derives implicitly this information? So the current project that I'm working on, it's like ontology also for MOPs, is part of the big the World Avatar project. And this is actually a universal digital twin that models real-world phenomena. So what we actually see is that we have interoperable way connection of this type of ontology to the onto species, but this is not all, because normally when you have a chemical development process, you would like to also to see how, for example, particular chemical in future can be part of industry process, or for example, what will be the cost for production, for energy costs, or for example, what will be its impact on the environment. So you would like to put this one in one ecosystem. So this is the World Avatar. At this moment in the World Avatar, there are 18 assembly models, and you can see these 18 assembly models. 2 minutes. Oh, shit. I have to be very quick. So these assembly models actually are representative of 151 structures. So what we actually have developed is that we have an algorithm. This algorithm allows us first to see the assembly model, then we query for the MOPs. After we have the MOPs, we actually get the chemical building units, and we put them in 2 bins. And then we can combinatorially find which kind of building units basically can create a MOP. But the issue with this is that we will find there will be always some chemical building unit that may have not been considered. So in this case, we develop a further loop where we actually find a network of structures, and we find which bins can actually, which sets of chemical building units can be exchanged between assembly models. So in terms of generic building units, we can see that there are 7 instead of 8, and simply because pentagonal planar it's not really commonly found. But we actually see that the algorithm has successfully found that generic building units, chemical building units that act as square planar can be easily shared between different assembly models. But once we go to something like 2 band, we actually start to separate those, and this is also linked to the hedral angles. So that means we will not propose an incorrect structure. So we can see that the previous knowledge, we have 150 instances, and using algorithm 1, we can propose 507 new instances which are derived. And once we go to algorithm 2, the full space converges to 1,418. So what does it mean? What is the implicit knowledge? For example, we have a particular structure. A chemist will say, how would you scale it up? Well, we will put a spacer. And this is basically what we actually see, that this is what actually we see that this is being proposed. So it's found. On the other hand, basically we have another structure which is actually more of like the large symmetrical ones, and then the question would be what kind of legal modification can be proposed. And this is, for example, in this case, a new instance is being proposed where, for example, one of these hydrogen atoms is replaced by bromine. So in general, we have conceptualized assembly models. We have also curated MOPs and built a knowledge graph on those. We have ontologically represented MOPs, and we have now a software agent that can map the chemical space. We use similar approach to target some other metal-organic hybrids, and we will try to connect the current work with the ongoing Marie question answering system for chemistry. I would like to thank my founders, and I would like to thank you for your attention. Thanks.